Okay, good day. This is Math 130 Intro to Statistics. I'm Professor McCauley. This is lesson number 12, Counting and Probability. Let's get to it. First, today we are going to find the number of ways a group of objects can be arranged in order. Then we're going to find the number of ways to choose several objects from a group, ignoring order. And then we're going to find the number of ways to choose several objects from a group in order and talk about the probabilities that go along with that. So first thing, a permutation is an ordered arrangement of objects. The number of permutations of n distinct objects is not n with an exclamation. It is n factorial, which is this notation here. And n factorial is the product of n and all of the positive whole numbers that are less than n. And there is one special case. 0 factorial is 1. So if you are seen to or asked to give 5 factorial, 5 factorial is just 5 times 4 times 3 times 2 times 1, which is 120. Now, you can do that in your graphing calculator, and more often than not, you will do the graphing calculator because these numbers are going to get very large very quick. So let's show how we're going to do that. If you hit the math button, and you'll notice that there's math, number, complex, there's some probability, and if we arrow over to that, you'll see that the fourth one is the exclamation point for factorial. We also have this NPR and NCR, which we will also be using today, and we'll be discussing that in the future. But if you actually want to use a factorial, you kind of have to plan ahead just a little bit. So if I want to do 5 factorial, I have to go 5 first, then I'm going to hit the math button, then I'm going to arrow over to probability, I'm going to hit the 4 button, hit enter, and that's how I get my 120. The next thing, permutations of n objects taken r at a time, is the number of permutations of n distinct objects taken r at a time is given by this equation here. You're not going to be asked to use that particular equation because we're going to use the graphing calculator. So you're never going to have to memorize this equation, but we are going to do it in the graphing calculator. So always make sure that n has to be greater than r because you can't take more objects than what there are in your group. So just as a instance, or as a simple example, you have 10 digit start over. You have 10 digit stickers, 0 through 9. How many ways can you order those three stickers? So basically what they're doing is they're saying you put all of the digits 0 through 9 in a hat and you pull them out 3 at a time. How many different ways can you arrange all of those stickers? So in one pull you could get 9, 8, and 7. On another pull you could get 9, 8, and 5. So that's what we're arranging here, and it is a permutation. It is 10 I did say it was a permutation. It's going to be 10 permutations of 3, and we're going to put that in the graphing calculator. Now again, when you're doing a permutation or a combination in the graphing calculator, you kind of have to plan ahead. We're going to type in that 10 first. We're going to hit that math button. We're going to bop over to probability again. We're going to hit 2 for NPR, and then we want to have 3 and 720 different ways that you can order those 3 stickers. All right. Distinguishable permutations. The number of distinguishable permutations of n objects, where n1 are of one type, n2 are of another type, and so on, will be n factorial over n sub 1 factorial times n sub 2 factorial, all the way up to n sub k factorial, where the sum of these different types add up to the total n possible. So just as an example, how many different ways can you order the letters in the word Mississippi? Now, we're talking about distinguishable permutations, things that you could tell the difference between. If I switch these two S's, you wouldn't be able to distinguish that from the original problem. But if I said MSISISSIPPI, we would have a distinguishable permutation. So if I count up all of the values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there are 11 values. So our n is going to be 11. Now our m's, well, our m's would be n sub 1. Now m's, there's only one m sub 1, so that would be a 1. Now 1 factorial is 1, so we're probably not going to write it. Our i's, we have 1, 2, 3, 4 i's, so n sub 2 is going to be 4. S's, we have 1, 2, 3, 4 S's, so S's, it would be n3. There are 4 of those, and P's, there would be n sub 4, and there are 2 of those. And now we've counted up all of the values. 1 plus 4 plus 4 plus 2 is 11. And so the different orderings would be 11 factorial all over 1 factorial, but we're not going to write that. So 4 factorial times 4 factorial times 2 factorial. And we're going to make that calculation. All right, so let's go to the graphing calculator. We're going to hit that 11, and then we're going to hit the math. We're going to go over to probability. We're going to hit 4 for that factorial. We're going to hit the divide key. Now, we have to multiply all of these together before we hit the enter key. So you got to be careful here. You need to put a parenthesis down here, or else it'll just go 11 divided by the first one and then multiply by the other values. So we have a 4 factorial. Oops. So I hit my math, go over to probability, hit 4 for that factorial times another 4 factorial. So go over to probability, hit 4 for that factorial times 2 factorial. So math, go over to probability, hit 2 there. Oops, I didn't want that. So we want to delete all that. We're going to have a 2, and then math over there, hit 4 to get the factorial there. So now we have 11 factorial over 4 factorial, 4 factorial, 2 factorial, and that is 34,650 different permutations. So I already forgot. 34,650. 34,650 different ways. All right. Moving on. Combinations. Combinations of n objects selected n at a time. The number of combinations of R objects selected from a group of n objects without regard to order is this NCR. Now you'll notice real quick a difference that it looks similar. Remember in permutations, we had n factorial over n minus r factorial, but combinations adds this additional r factorial. Now the reason that they do that is because order is unimportant. So just as a real quick example, if I were to order, just go say 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. I think I did those. Yeah. So this in permutations is 6 orderings. But in combinations, the order doesn't matter. It just matters that you have the 3 values. So in combinations, this just represents 1 ordering. So just as long as you have those 3 values. All right. So here's an elementary example. How many ways can you get a committee of 4 people to be chosen from a group of 10 people? So a committee, if you're on the committee, you have the same power as any other person in the committee. So it doesn't really matter what order you've been picked in. As long as you're on the committee, you are on it. So in this particular instance, instead of 10p4, it's going to be 10c4. And we're going to put that in the graphing calculator the same way. So we're going to hit our 10. I'm going to hit that math button. We're going to go over to probability. We're going to hit 3 for combinations. We're going to hit that 4 button, hit enter, and there are 210 different ways that a committee can be formed from 10 people choosing 4 at a time. All right, so using permutations and combinations and probability. The McCully clan leadership consists of 120 members. From those members, they select a Grand Poobah, a Vice Poobah, and a Treasurer each year. If selected at random, what is the probability that the members who already hold those positions should be selected again? So probability that members re-elected. All right. Well, if you want the same people in the Grand Poobah, the Vice Poobah, and the Treasurer, there is only one way that you can select them. But because the leadership positions aren't a committee, certainly the Grand Poobah, the Vice Poobah, and the Treasurer have different powers. There are 3 different offices that we are selecting from 20 members. That is going to be a permutation of 20p3. And we're going to put that in our graphing calculator. We'll go 1, we'll go divided by 20, hit that alpha, or the math button, not the alpha button. Oops, I need to delete that. I did that incorrectly, sorry. Hit that math button, go over to probability, hit the 2, and then we are selecting 3 people. And so this probability is pretty darn small. And so again, if you see this notation with this E, you can think of this as scientific notation. So this is 1.46, well, what will be 2 times 10 to the negative 4 power. So we would move our decimal place 4 places. So there would be 1, 2, 3, 4. So we've got to add 3 zeros in there before we get to a significant figure. So 0.123, and then let's rewrite it. So 146. That's a pretty small chance. All right, next. Example, in poker, getting 5 cards in the same suit is called a flush. What is the probability of being dealt 5 hearts? So probability 5 hearts. All right. Well, hearts, there's only 13 hearts in a deck, so 13. And in cards, it's a little bit different than the last example, because what's the first thing that you do when you get a hand of cards? You reorder them so that you can play them the way that you want. So it doesn't really matter what order that you get the cards. And since it doesn't matter what order you get the cards, we're going to talk about a combination of the 5 cards that we're getting. So these are the favorable outcomes, the 13 hearts chosen 5 at a time, over, well, there are 52 cards in a standard deck, and we are still choosing 5 of them. So here are our favorable outcomes. Here are our total outcomes. We can do that calculation fairly quickly. 13, math, go over to probability, hit that 3 for the combinations. We're choosing 5, and we're going to oops, we need to hit our right arrow key so that it comes up. Hit the divide bar, and now it is 52 math fraction, or we need to go over to probability. Hit that 3, and we're choosing 5. And again, this is going to be pretty small. And so this one, again, we have 4 decimal places. And so 00491, 0.000491, 495, excuse me, is what that should be. 495. And this is to be fair, this is the probability that you get dealt a flush. Now, in most games of poker, there's ways that you get more cards. You can either discard a couple, or if you're playing like Texas Hold'em, you're actually playing from 7 cards. And so playing for 7 cards certainly increases your chances of getting a flush. All right. So, an example, an evil genius hides 4 poison candy-coated chocolates, and I used candy-coated chocolates because I didn't want to break any copyright rules. So, there are 4 poison candy-coated chocolate in a bowl of 100 candy-coated chocolates. If you were to take 5 candy-coated chocolates, what is the probability that A, you would get exactly 1 poisoned candy-coated chocolate, B, no poison candy-coated chocolates, or C, at least 1 candy-coated chocolate? Well, let's see. Probability, exactly 1. All right, so we want exactly 1 of 4. So again, this is going to be an instance where combinations are used because it doesn't matter when you took that poison one. If it's in your hand when you chose those 5 candies, it's in your hand. So 4 chosen one at a time, exactly 1 of the 4 poison ones. And then from the 96 left, you're going, since we're choosing 5, we still have to choose 4 more over. There are 100 chocolates in the bowl, and we're going to choose 5 of those. So again, we're going to do the graphing calculator. And so since we want this whole, we want to multiply these two before we divide, we're going to put parentheses around it, although I don't think we'll need them. So for math, go over to probability, hit 3. We're choosing one of those. We're going to push our right arrow key so that it gets out of that subscript. And then we're going to hit times, and then it'll be 96, and then hit the math button, go over to probability, hit that 3, and we'll hit the, we need 4 more of those. And so hit our right arrow key again to come up. We'll close that parenthesis for the top, and then we're going to divide by. There are 100 candies in the dish, and we are choosing 5 of them. And so the probability that you would get exactly 1 of the 5 is 17.649%. We'll call it 0.17649, or 17.649%. That's a 4. Let's check, make sure I did that right. 649. Yep. Okay. So that's part A. Part B, that you choose no chocolates, no poison. All right. Well, that's pretty easy. There are 96 chocolates that have no poison in them, and we need to choose all 5 of those from 100 total chocolates in the bowl, and we're choosing 5 of those. So that's a little bit easier one. So 96, hit the math button, go over to probability, hit 3. We're choosing 5 of those, hit our right arrow to get out of the subscript, hit divide, and then we'll go 100, hit math, over to probability, hit 3. We're choosing 5 of those. And so there's an 80, let's see, 0.812 or 81.812, 0.812 or 81 point, let's see here, it'll be 188%. 88% chance that you would get no poison. So C, the probability that you get at least 1, means what is the probability that you got either exactly 1, exactly 2, exactly 3, or exactly 4 of those total candies. So this is really we could do it in a couple different ways, but the easiest way is to say that this is the negation of the no poison. So if you don't have a poison one in your hand, you have at least 1 poison one in your hand. And so we can do a complement here and say that this is 1 minus the probability of no poison, which in this case would be 1 minus 0.81. Well, we'll do it 8. We'll just, on the graphing calculator, we'll go 1 minus second answer, and then that puts that into there. And we hit enter, and so 0.18812, which is 0.18812, or 18.812%. So there's an 18% chance that if you stuck your hand in that bowl and pulled out 5 candies, you get at least one of the poison ones. So that's too big of a percentage for me, but what are you going to do? Anyway, so that brings us to the end. Our Marvel fun fact of the day: in the MCU movies, Iron Man's suit is almost entirely CGI. Robert Downey Jr. Usually just wears "quote unquote" the shoulder pads, part of the arm and part of the arms. The remainder is filled in by a computer. That's all I got for today. Have a good one. Bye.